Dear friend, welcome to this gentle journey into the heart of reality. In this video, we'll explore the smallest known particles in the universe: quarks, leptons, bosons, and the mysterious possibilities that lie beyond. Let your mind drift and your curiosity awaken as we unravel the elegant simplicity of the quantum world. Let's begin this calming exploration together. Chapter 1: Introduction. The quest for the smallest pieces of nature. From the earliest days of human curiosity, people have sought to understand what everything is made of. It is a question that has driven our progress from ancient philosophy to modern physics. What are the fundamental building blocks of reality? This quest to understand the most basic components of nature has shaped every aspect of science, from the smallest grains of sand to the vast cosmic structures that fill the universe. The search for the smallest particles began long before the scientific method took hold. Ancient Greek philosophers such as Democritus and Leucippus imagined that matter must be composed of indivisible units called atomos, meaning uncuttable. These early ideas were poetic and intuitive, born from the observation that objects can be broken into smaller and smaller pieces, yet surely there must be a point at which further division is impossible. Although these concepts lacked the precision and rigor of modern science, they hinted at a profound truth: nature has a hidden structure beneath the world we see. For centuries, the idea of atoms remained a philosophical curiosity. It wasn't until the 19th century that experimental evidence began to support the notion of indivisible particles. Chemists and physicists such as John Dalton and J.J. Thomson demonstrated that substances could be broken down into distinct, repeatable components, elements that combine to form all known materials. This was the beginning of the atomic theory as a scientific framework rather than a philosophical musing. However, even as atoms became the cornerstone of modern chemistry, they did not remain the smallest known pieces of nature for long. In the early 20th century, experiments with electricity and radiation revealed that atoms themselves were made of even smaller components. The discovery of the electron by J.J. Thomson in 1897, followed by Ernest Rutherford's work in the early 1900s, showed that atoms were not indivisible at all. Instead, they contained a dense, positively charged nucleus surrounded by a cloud of negatively charged electrons. This revolutionary insight led to the development of quantum theory, a framework that fundamentally changed our understanding of matter. The quantum world is a realm where classical intuition breaks down, where particles are described by probabilities and uncertainty. It is here that the smallest pieces of nature reveal themselves, not as solid billiard balls, but as shimmering clouds of possibility. As scientists probed deeper, they discovered that the atomic nucleus itself was not fundamental. Protons and neutrons, the particles that make up the nucleus, are in fact composed of even smaller particles called quarks. This realization, which emerged in the 1960s and 1970s through the work of physicists such as Murray Gell-Mann and George Zweig, marked another profound shift in our understanding of matter. Quarks, bound together by the strong nuclear force, form the protons and neutrons that in turn build up the elements of the periodic table. Alongside quarks, physicists identified a family of particles called leptons, which include the well-known electron and the elusive neutrino. These particles, together with the quarks, make up the standard model of particle physics, the current best theory of the fundamental building blocks of the universe. The standard model describes not only the particles themselves, but also the forces that govern their interactions: electromagnetism, the weak nuclear force, and the strong nuclear force. The only force it does not fully encompass is gravity, which remains the domain of Einstein's general relativity, a theory of curved spacetime rather than particles. The standard model is a triumph of modern physics, a tapestry woven from decades of theoretical insight and experimental confirmation. It has predicted the existence of particles that were later found in experiments, such as the Higgs boson, discovered in 2012 at CERN's Large Hadron Collider. The discovery of the Higgs boson confirmed the existence of the Higgs field, a pervasive field that gives mass to fundamental particles. This field is like a cosmic sea in which particles swim, their interactions with the field determining their mass and behavior. Yet even the Standard Model is not the final word. Physicists know that it is incomplete. It does not explain gravity at the quantum level, nor does it fully account for the dark matter that seems to outweigh visible matter in the cosmos. There are hints of deeper structures, supersymmetry, extra dimensions, and string theory, ideas that push the boundaries of what we can observe and test. These questions drive the continuing search for even smaller particles and more fundamental forces. This journey is not just a scientific endeavor, but also a profound human adventure. To search for the smallest pieces of nature is to ask about the very fabric of reality. It is to wonder whether there is an ultimate foundation to the universe, or whether each discovery only reveals deeper and more subtle layers. Our tools for this search have grown ever more powerful. From early cathode ray tubes to modern particle colliders, physicists have created machines that can smash matter into its tiniest pieces and reveal their secrets. Detectors like those at CERN's Large Hadron Collider are marvels of engineering, built to capture fleeting traces of particles that exist for only fractions of a second. These machines allow us to peer deeper into the heart of matter than ever before. Experiments have shown that the quantum world is a place of constant activity. Even empty space, in the quantum sense, is never truly empty. Virtual particles flicker in and out of existence, a restless energy that hints at a deeper truth about reality itself. The quantum fields that fill the universe are not static backdrops, but dynamic participants in the cosmic story. Each of the fundamental particles has its own unique properties and role in the dance of the cosmos. Quarks build the structure of protons and neutrons, held together by the gluons of the strong force. Electrons, the lightest charged lepton, orbit nuclei and define the chemistry of the universe. Neutrinos pass almost invisibly through matter, whispering hints of processes deep within stars and supernovae. Photons carry light and energy across the vast reaches of space, illuminating the universe for our eyes and our instruments. The W and Z bosons mediate the weak force, enabling the transformations that power the sun and the radioactive decay that warms the Earth. The Higgs boson, a fleeting particle born of the Higgs field, completes the Standard Model's framework, ensuring that particles have mass and that the universe has structure. Yet despite our growing understanding, the smallest pieces of nature remain full of mystery. Why do the fundamental forces have the strength they do? Why do quarks come in 6 flavors? Why does the Higgs field exist at all? Each answer seems to open the door to new questions, new frontiers of knowledge. This relentless curiosity is part of what makes the study of the smallest particles so compelling. It is not just about cataloging particles or forces. It is about glimpsing the underlying simplicity and symmetry of the universe. It is about seeing how everything we experience, from the air we breathe to the light of distant galaxies, emerges from the interactions of particles so tiny that they can only be described by the mathematics of quantum theory. In this video series, we will explore the most fundamental particles known to physics: quarks, leptons, photons, gluons, W and Z bosons, the Higgs boson, and the tantalizing idea of gravitons. Each chapter will take you on a gentle scientific journey, describing how these particles were discovered, what they do, and how they fit into the grand tapestry of the cosmos. We will see how the smallest pieces of nature reveal themselves not in isolation, but in relationships, interactions, and fields. we will discover how experiments and theory come together to give us glimpses of an invisible world, one that is woven into everything we see and touch. As we begin this journey, it's worth pausing to consider what it means to search for the smallest pieces of nature. On one level, it is a technical challenge, a question of building ever more sensitive instruments and more powerful colliders. But on another level, it is a philosophical quest, a reflection of our deep need to understand our place in the universe. For as we study the smallest scales, we find that we are not separate from them. The atoms of our bodies, the photons that strike our retinas, the neutrinos streaming through us, all are part of the same quantum dance. The search for the smallest pieces of nature is also a search for ourselves, a reminder that we are connected to the very heart of reality. And so, as we embark on this exploration, let us carry with us a sense of wonder and humility. The smallest pieces of nature are not merely technical curiosities. They are clues to a deeper order, a glimpse of the unity that underlies the diversity of the cosmos. In their patterns and interactions, we see echoes of the infinite complexity and beauty of the universe, a beauty that in the end reflects something profound about our own place in the grand cosmic story. Chapter 2. Quarks, the building blocks of protons and neutrons. When we peer deeper into the atomic nucleus, beyond the familiar protons and neutrons that shape the periodic table, we encounter an even more fundamental layer of matter, the realm of quarks. These elusive entities are among the smallest known building blocks in the universe, forming the very essence of what we consider to be solid and tangible. They are not particles we can isolate or hold in our hands. Instead, they are the fundamental ingredients that, when bound together, make up the atomic heart of all matter. Quarks were first proposed in the early 1960s by physicists Murray Gell-Mann and George Zweig, who independently suggested that protons, neutrons, and many other particles called hadrons could be explained if they were themselves composed of smaller units. This idea arose from the confusion of the so-called particle zoo, a seemingly endless list of new particles discovered in cosmic rays and particle accelerators. Rather than viewing each new particle as fundamental, Gell-Mann and Zweig proposed a simpler scheme, that all these hadrons were combinations of just a few elementary components. What began as a theoretical convenience soon took on the weight of experimental reality. Quarks explained why certain particles behaved the way they did and why others could not exist. Over time, their existence became one of the cornerstones of the standard model of particle physics, a framework that unifies our understanding of the smallest constituents of the cosmos. Quarks are unlike any particles we experience in daily life. They possess a property known as fractional electric charge, a feature that sets them apart from the familiar whole charges of protons and electrons. For example, the up quark carries a charge of positive 2/3, while the down quark has a charge of negative 1/3. These unusual charges ensure that when quarks combine in groups of 3, the result is a whole integer charge, as seen in protons and neutrons. One of the most fascinating aspects of quarks is the way they are bound together. Quarks are held inside protons and neutrons by the strong nuclear force, one of the 4 fundamental forces of nature. Unlike the familiar electromagnetic force, which weakens as distance grows, the strong force behaves in an unusual and counterintuitive way. The more you try to pull quarks apart, the stronger the force becomes. This phenomenon is known as confinement, and it is why no quark has ever been observed alone in nature. The force that binds quarks together is mediated by particles called gluons, aptly named for their role as the glue of the strong interaction. Gluons carry not only the force but also a property called color charge, an abstract quality unrelated to visual color. Each quark comes in one of 3 color charges, red, green, or blue, and only combinations that blend these charges into a neutral color are stable. It is a curious and elegant rule of nature, akin to a cosmic game of balance and harmony, ensuring that the universe maintains its structural integrity. Inside a proton or neutron, quarks are in constant motion, exchanging gluons and interacting with each other in a dynamic and intricate dance. This inner life is not static, but rather a seething ocean of energy and interaction. The quarks themselves are point-like, but the forces that hold them together create a rich and complex structure that gives protons and neutrons their size and mass. Interestingly, much of the mass of protons and neutrons, and therefore most of the visible mass in the universe, does not come directly from the quarks themselves. Instead, it emerges from the energy of the strong interaction. According to Einstein's famous equation, energy and mass are two sides of the same coin. The energy stored in the binding of quarks and gluons manifests as the mass we measure in experiments and observe in the world around us. This realization underscores a profound lesson of modern physics. What we consider to be solid and material is, at its most basic level, a manifestation of energy and dynamic forces. Quarks provide the building blocks, but it is the ceaseless exchange of gluons and the confinement of color charge that creates the mass and stability of matter. Beyond the up and down quarks that make up protons and neutrons, the Standard Model includes 4 more quark types: strange, charm, bottom, and top. These heavier quarks play a vital role in high-energy physics, even though they are not found in ordinary matter. In particle accelerators, when protons are smashed together at near-light speeds, these heavier quarks can be created briefly before decaying into lighter forms. Their fleeting existence offers glimpses into the deep symmetries and relationships that bind all matter. The top quark, the heaviest of them all, was discovered only in 1995, a triumph of collaboration and technology. Its discovery confirmed the completeness of the 3 families of quarks in the Standard Model, reinforcing the theory's predictive power. Though the top quark's lifetime is fleeting, its study helps physicists probe the limits of the known and search for clues of physics beyond the Standard Model. Quarks are also responsible for the diversity of hadrons we find in nature. By combining in different ways, they create an array of particles: protons, neutrons, and their cousins like the lambda, sigma, and omega baryons. They also form mesons, quark-antiquark pairs that play a vital role in mediating the residual strong force between nucleons. These combinations are described by the elegant mathematics of quantum chromodynamics, a theory that has been tested to extraordinary precision. Yet even as we probe deeper into the behavior of quarks, their existence challenges our intuition. Unlike electrons, which can exist as isolated particles, quarks are forever confined within larger structures. This feature makes them almost ghostly, present everywhere, yet never directly observed. We know of them only through the hadrons they compose and the indirect signatures they leave in high-energy collisions. One of the most compelling ways we learn about quarks is through experiments like deep inelastic scattering, in which high-energy electrons are fired at protons. In these collisions, the electrons probe the inner structure of protons, revealing evidence of smaller constituents within. Such experiments have confirmed that protons and neutrons are not solid objects, but dynamic assemblies of quarks and gluons. These discoveries have practical consequences as well. In the early universe, quarks roamed freely in a state known as quark-gluon plasma, a searing soup of fundamental particles that existed just moments after the Big Bang. Modern experiments at facilities like the Relativistic Heavy Ion Collider and the Large Hadron Collider recreate these primordial conditions for fleeting instants, allowing us to study how matter as we know it emerged from this early chaos. By understanding quarks, we gain a window into the birth of the universe itself, a glimpse of how structure arose from the seething energy of the Big Bang. This is not just a curiosity for physicists. It is a testament to the unity of all things, from the smallest scales to the grandest cosmic structures. Yet as we contemplate these smallest known building blocks, deeper questions remain. Why do quarks come in exactly 6 flavors? Why does nature prefer this specific arrangement? Why does the strong force behave as it does, growing stronger with distance rather than weaker? These questions hint at layers of reality still hidden from view, challenging physicists to push their theories and experiments to ever greater precision. Quarks also challenge our sense of what it means for something to be fundamental. Are quarks the end of the line, the ultimate building blocks, or are they themselves made of even more subtle structures? Theories like string theory suggest that quarks may be vibrations of one-dimensional strings, tiny filaments whose oscillations determine the properties of the particles we observe. If this is true, then the quark is not the smallest piece of nature, but a window into a deeper, more unified picture of the universe. For now, quarks remain our best picture of the substructure of matter. They represent both an achievement of human curiosity and a reminder of the profound complexity that lies beneath the surface of everyday life. Every proton in your body, every neutron and every atom is a dynamic interplay of quarks and gluons, bound together in an endless dance of energy and interaction. As we close this chapter, it is worth pausing to reflect on the journey we have taken. We began with atoms, then discovered the protons and neutrons within. Now, with quarks, we stand at the frontier of the known, peering into the heart of matter itself. And yet, even here, mysteries remain. The quark is both a triumph of discovery and a reminder of our limitations. It is a testament to how far we have come and how much there is still to learn. In this quiet realization lies an existential comfort. For all our probing, for all our questions, we find that the universe is more intricate and interconnected than we could have imagined. The quarks that swirl within protons and neutrons are not distant abstractions. They are part of you and me, woven into the fabric of life and the cosmos. As we continue this journey into the heart of matter, we find not only the pieces of nature, but also a deeper understanding of our own place in this endless, unfolding universe. Chapter 3. Leptons, the familiar and the elusive. When we turn our gaze away from the swirling cores of protons and neutrons, where quarks and gluons hold court, we find a family of particles that is both familiar and deeply mysterious. The leptons. These particles are, in a sense, the other half of the standard model of particle physics. They are the quiet companions to quarks, fundamental in their own right and essential to the workings of the universe. Leptons are distinguished by their lack of color charge, which means they do not participate in the strong nuclear force. This makes them fundamentally different from quarks, which are bound together by the color-charged gluons. Instead, leptons are governed by the electromagnetic force and the weak nuclear force, two of the other fundamental interactions that shape the cosmos. Among the leptons, the electron is the most familiar and ever-present companion in our daily lives. Every time we flip a switch, charge a battery, or watch light dance across a screen, it is the electron at work. A particle that is so common we might forget it is also one of the most fundamental. It is a particle of pure simplicity. No internal structure, no swirling dance of quarks or gluons, just a point-like entity that carries negative electric charge and a tiny mass. The electron's role in nature is profound. It orbits atomic nuclei, defining the size and shape of atoms. Its negative charge balances the positive charge of protons, creating the electrostatic glue that holds matter together. In chemical reactions, it is the electron that is transferred, shared, or rearranged, weaving the tapestry of chemistry that underlies biology and technology alike. Yet the electron is not alone. It has two heavier cousins, the muon and the tau, each sharing the same charge and spin, but with much greater mass. These particles do not linger in the world of ordinary matter. They are born in high-energy events and decay rapidly into lighter particles. The muon, with a mass about 200 times that of the electron, lives for only a fraction of a second before decaying, while the tau, even heavier, decays in an even briefer instant. The existence of these heavier leptons was a surprise when first discovered. The muon emerged in cosmic ray experiments in the 1930s, detected in the showers of particles produced when high-energy cosmic rays strike Earth's atmosphere. Its discovery puzzled physicists, who had not anticipated a heavier electron-like particle. The tau lepton, even more fleeting, was identified decades later in collider experiments, each discovery expanding the zoo of fundamental particles. Though they share the same electric charge, the muon and tau's greater masses mean they play different roles in the cosmos. They are not part of ordinary atoms, nor do they participate in the familiar chemistry of life. Instead, they are born in the high-energy crucibles of particle collisions and cosmic events, offering a window into the behavior of matter under extreme conditions. Alongside these charged leptons are the most elusive of all, the neutrinos. These ghostly particles are the lightest of the leptons and perhaps the most enigmatic. Neutrinos carry no electric charge and interact only through the weak force and gravity. This means they can pass through light years of lead without being stopped, slipping through matter almost as if it were not there at all. Neutrinos come in three varieties: electron neutrinos, muon neutrinos, and tau neutrinos, each associated with one of the charged leptons. Their masses are incredibly small, so slight that for decades physicists believed them to be zero. Recent discoveries, however, have shown that neutrinos do have mass, albeit incredibly tiny. This revelation has profound implications for our understanding of the universe, suggesting that the standard model is incomplete and pointing to physics beyond its boundaries. The journey to understanding neutrinos has been long and challenging. They were first proposed by Wolfgang Pauli in 1930 as a solution to an apparent paradox. In radioactive beta decay, electrons seem to emerge with a puzzling spread of energies, violating the conservation of energy. Pauli suggested that an unseen particle must be carrying away the missing energy, and so the neutrino was born as a theoretical entity. It would take a quarter of a century before neutrinos were directly detected. In 1956, Clyde Cowan and Frederick Rhines succeeded in observing neutrinos from a nuclear reactor, confirming their existence and opening a new chapter in particle physics. Since then, experiments have revealed the astonishing properties of these elusive particles. One of the most surprising discoveries about neutrinos is that they can change from one type to another as they travel, a phenomenon known as neutrino oscillation. This discovery showed that neutrinos have mass, a result that the original formulation of the Standard Model did not anticipate. It hints at a deeper structure to the universe and opens the door to new theories that could unify the known forces of nature. Neutrinos are produced in vast numbers in the cores of stars, including our Sun, as hydrogen fuses into helium and releases energy. Billions of solar neutrinos pass through every square centimeter of your body each second, a silent rain of particles that speaks to the universality of nuclear processes across the cosmos. These particles, born in the hearts of stars, provide a direct connection between our own bodies and the luminous engines that light the night sky. On Earth, neutrinos play a role in radioactive decay, a subtle presence in the transformation of elements that shapes the heat of the planet's interior. In the cataclysmic deaths of massive stars, when supernovae blaze forth with the energy of entire galaxies, neutrinos carry away most of the energy, a flood of ghostly messengers that whisper of cosmic violence. Despite their abundance, neutrinos remain extraordinarily difficult to study. Their feeble interactions require enormous detectors such as the massive water tanks of Super Kamiokande in Japan or the vast arrays of ice cube buried deep in the Antarctic ice. These experiments patiently watch for the faintest flashes of light produced when a neutrino occasionally collides with an atom. In these rare interactions, scientists glimpse the hidden world of these ghostly particles. For the charged leptons, the electron, muon, and tau, their interactions are better understood. The electron, as part of atoms, defines the chemistry of the world. The muon and tau, while fleeting, reveal the symmetry and structure of the Standard Model. Their heavier masses are not arbitrary, but arise from the Higgs field, the same subtle mechanism that gives mass to quarks and binds the fabric of matter together. Leptons interact through the weak force, a force that, despite its name, plays a vital role in shaping the universe. It governs processes such as beta decay, enabling the transmutation of elements and the release of energy that powers the sun and warms the earth. Without the weak interaction, the universe would be a very different place. A static expanse with no stars, no life, no evolution of elements. The weak interaction also illustrates a profound feature of nature. It violates certain symmetries that seem so natural in our daily experience. For instance, it does not respect mirror symmetry. It distinguishes left from right, an asymmetry woven into the fundamental laws of physics. This subtle violation hints at the deep complexity of the forces that govern the cosmos. As we explore the world of leptons, we find a realm that is both intimately connected to our lives and yet almost invisible. Electrons flow in every circuit, yet we never see them directly. Neutrinos pass through us by the billions each second, yet we remain unaware of their presence. Muons and tau particles flash into existence in high-energy collisions, a brief echo of the energies that shaped the early universe. In contemplating leptons, we are reminded that the universe is built from the interplay of the familiar and the mysterious. The electron binds atoms and fuels life, while the neutrino challenges our understanding of what it means to interact at all. The muon and tau hint at a deeper pattern, a family of particles that echoes the diversity and symmetry of the natural world. The study of leptons is more than a cataloging of particles. It is a journey into the hidden architecture of reality, a search for the principles that give rise to everything we see and touch. In their simplicity and their mystery, leptons reveal the elegance of the cosmos, a unity that emerges from diversity and complexity. And as we reach the end of this chapter, it is worth pausing to consider what these particles teach us, beyond the equations and the detectors. They remind us that the universe is not a static collection of objects, but a dynamic interplay of forces and interactions. Even the most familiar particles, like the electron, are part of a grander story, one that stretches from the heart of the atom to the edge of the cosmos. In the quiet of the night, as neutrinos pass silently through the Earth and electrons flow in circuits unseen, we find a gentle reassurance in the continuity of these processes. The smallest pieces of nature, so far removed from daily perception, are also the threads that bind us to the stars. In them, we glimpse both the precision of physics and the poetry of existence, a reminder that we are part of a universe whose beauty lies as much in its mystery as in its light. Chapter 4: Photons, the messengers of light. In the symphony of the universe, where quarks dance in protons and electrons hum in their orbits, there exists a particle that acts not as a note, but as the very music that carries it. This particle is the photon, the quantum of light, a messenger that travels across the cosmic expanse, linking distant stars and distant minds. The photon is the agent of light and electromagnetism, the most pervasive force in our daily lives and the most familiar companion in our perception of the cosmos. The photon is remarkable not only for its role, but also for its nature. Unlike the quarks and leptons we have explored, the photon is massless. It has no rest mass, and as a result, it travels at the ultimate speed limit of the universe, the speed of light. This speed is not merely a convenience, it is a fundamental constant woven into the fabric of space-time itself, a limit that defines causality and the structure of the cosmos. In everyday life, photons are the light we see, the warmth of the sun, the radio signals that carry our voices across continents. But these familiar experiences are only the visible manifestations of a much deeper reality. The photon is the mediator of the electromagnetic force, the fundamental interaction that shapes chemistry, biology, and the very structure of atoms and molecules. The story of the photon is intertwined with the story of light itself, a tale that stretches back to ancient times. Philosophers like Euclid and Pythagoras pondered the nature of vision and light, while medieval scholars debated whether light was a particle or a wave. It was in the 17th century that Isaac Newton and Christian Huygens offered competing theories. Newton envisioned light as a stream of particles, while Huygens argued for a wave-like nature. For centuries, this debate continued, each new experiment revealing new clues. In the 19th century, James Clerk Maxwell unified electricity and magnetism in his elegant equations, showing that light is an oscillation of electric and magnetic fields traveling through space. This wave theory of light explained a host of phenomena, from the colors of a soap bubble to the rainbows that adorn the sky after a storm. Yet as physicists delved deeper into the behavior of light, they encountered puzzles that the wave theory alone could not resolve. The photoelectric effect, in which light striking a metal surface releases electrons, resisted explanation by the wave model. In 1905, Albert Einstein proposed that light itself comes in discrete packets, quanta, each carrying a specific amount of energy. These quanta of light were the photons, and their existence bridged the gap between the particle and wave descriptions. This dual nature of photons, as both wave and particle, lies at the heart of quantum physics. A photon can interfere with itself, creating patterns of light and shadow in a double-slit experiment. Yet when it interacts with matter, it does so as a localized packet of energy, a particle that can be absorbed or emitted by atoms and molecules. This wave-particle duality is not just a curious feature, but a profound truth of the quantum world, a reminder that our classical intuition must give way to a more subtle understanding of reality. Photons have no electric charge and no mass, yet they carry momentum and energy. This allows them to exert pressure, a fact that may seem abstract but has real consequences in nature. The pressure of sunlight drives the tails of comets and can propel tiny spacecraft across the void, a gentle push from the photons streaming out of the sun. The photon's energy is proportional to its frequency, meaning that photons of different colors and types carry different amounts of energy. The visible spectrum is just a tiny sliver of the electromagnetic spectrum, which stretches from the low-energy radio waves to the high-energy gamma rays. Each part of this spectrum plays a role in the cosmos, from the microwaves that reveal the afterglow of the Big Bang to the gamma rays that mark the deaths of massive stars. In the life of an atom, photons are the means by which energy levels shift and change. When an electron in an atom transitions from one energy level to another, it emits or absorbs a photon, a flash of light that carries away the difference in energy. This is the origin of the spectral line seen in the light of stars, the fingerprints of the elements that compose them. These lines tell astronomers the chemical makeup of distant galaxies and the motion of stars across the heavens. The photon's role extends far beyond atomic transitions. In the quantum vacuum, even in the absence of real photons, virtual photons flicker in and out of existence, mediating the electromagnetic interaction between charged particles. This quantum dance underlies the stability of atoms and the repulsion or attraction that shapes the structures of molecules and materials. The photon is also the bridge between the infinitesimally small and the astronomically large. Light from distant galaxies, traveling for billions of years, brings us glimpses of the early universe. The cosmic microwave background, the faint afterglow of the Big Bang, is composed of photons that have traveled nearly unimpeded since the dawn of time, carrying with them the story of the cosmos in its infancy. In laboratories and observatories, physicists manipulate and measure photons with exquisite precision. Lasers, devices that produce coherent streams of photons, have become indispensable tools in modern science and technology. From the barcode scanners in grocery stores to the ultra-precise measurements of gravitational waves, lasers harness the unique properties of photons to explore and shape the world. Yet for all their familiarity, photons remain full of mystery. In quantum electrodynamics, the theory that describes the interactions of light and matter, photons are treated as excitations of the electromagnetic field, ripples in a field that permeates all of space. They have no rest frame, no internal structure, and exist only as quanta of energy and momentum. This field-theoretic view of photons reveals a deep truth about the nature of reality. Particles and fields are two sides of the same coin. What we perceive as a particle is really a localized disturbance in a field that extends everywhere. The photon is not a little bullet of light, but a manifestation of the electromagnetic field's endless reach, a traveling disturbance that carries energy and information across the cosmos. In this way, the photon links the tangible world of matter with the intangible world of fields, offering a glimpse of the unity that underlies all of physics. It is a reminder that the smallest pieces of nature are not static building blocks, but dynamic processes, patterns of interaction and relationship. In our daily lives, we are bathed in a sea of photons. The light of the sun that warms our skin, the glow of a candle in the darkness, the screens that connect us to each other across oceans, all are mediated by photons, the tireless messengers of the universe. They shape our perceptions and our technologies, weaving the visible world from their ceaseless dance. And yet, as we contemplate the photon, we find a paradox. It is a particle that is never at rest, a wave that is never still, a quantum of energy that carries the memory of distant stars and the warmth of a human touch. It is both the most familiar and the most elusive of nature's gifts, a testament to the subtlety and beauty of the quantum world. In the quiet of the night, as we look up at the stars, it is the photon that carries their ancient light to our eyes. Each photon has traveled across the cold emptiness of space, bearing witness to the birth and death of suns, the collisions of galaxies, the expansion of the universe itself. In this journey of light, we find not only a story of physics, but a story of connection. A reminder that we, too, are part of a universe where even the smallest quanta of energy are woven into the grand tapestry of existence. As we conclude this chapter, let us pause to reflect on what the photon reveals to us. It shows that the universe is not a static collection of things, but a dynamic interplay of energy and information. It teaches us that even the smallest particles can carry the weight of cosmic history, that light is both a measurement and a memory, a wave and a whisper from the distant past. In the flicker of a candle or the shimmer of starlight, we glimpse the photon's journey. And in that journey, we glimpse ourselves, woven from the same quantum threads, part of the same endless song of the cosmos. Chapter 5. Gluons, the strong force glue. In the subatomic realm, where particles move to the quantum music of the universe, gluons stand as the silent architects of matter's durability. These massless quanta of the strong nuclear force are unlike anything encountered in the macroscopic world. They are the cosmic glue that binds the smallest known constituents of protons and neutrons together, ensuring that the vast structures of galaxies and the quiet matter of our bodies can exist at all. The strong nuclear force, which gluons mediate, is the most powerful of the four known fundamental forces of nature. It is so strong that it overcomes the repulsion between the positively charged protons within atomic nuclei, binding them with a resilience that defines the stability of ordinary matter. Yet, unlike gravity or electromagnetism, the strong force's behavior is complex and at times counterintuitive, a testament to the elegant yet mysterious nature of quantum chromodynamics. Gluons themselves are massless, traveling at the speed of light, and possess a spin of 1, making them vector bosons. But they are far more complex than the photon of electromagnetism. While photons are electrically neutral and do not interact with one another, gluons carry a property known as color charge, a unique feature of the strong force. This color charge is not a literal color, but an abstract quantum property that comes in 3 types: red, green, and blue, along with their corresponding anticolors. Quarks each possess one of these color charges, and gluons act as the agents that swap and mediate these charges during interactions. The presence of color charge in gluons means that they themselves participate in the strong interaction, unlike the photon, which is uncharged and interacts only with charged particles. This self-interaction is a crucial aspect of the strong force's character. When gluons are exchanged between quarks, they not only mediate the force but also contribute to the creation of a dynamic, self-sustaining field that fills the confined volume of a hadron. This dance of color charges is not a simple exchange, but a swirling sea of activity. Within every proton and neutron, quarks are in constant motion, bound together by the continuous exchange of gluons. These gluons in turn interact with each other, forming a tightly woven web of energy that keeps quarks confined. The result is a complex and beautiful system, a microcosm of constant change and interdependence. The notion that the strong force grows stronger as quarks are pulled apart, an effect known as confinement, defies everyday experience. In familiar forces like gravity or electromagnetism, the strength diminishes with distance. But in the realm of quarks and gluons, it is as if the more you pull, the more the universe resists. This property ensures that quarks remain permanently locked within protons and neutrons, preventing the existence of free quarks in isolation. Confinement can be visualized through the idea of flux tubes, narrow regions of color electric field that connect quarks. As quarks are separated, these flux tubes stretch, storing energy like a taut spring. When enough energy is accumulated, it becomes energetically favorable for the flux tube to snap and create a new quark-antiquark pair, forming new hadrons instead of allowing a quark to exist alone. This perpetual reshuffling preserves the integrity of color charge and illustrates the profound stability that emerges from the strong interaction. To comprehend the strong force quantitatively, physicists turn to the framework of quantum chromodynamics, a quantum field theory that encapsulates the principles governing quarks and gluons. QCD is a gauge theory, one that depends on local symmetries, and it is this structure that allows it to accommodate the intricate self-interactions of gluons. But the very richness of QCD makes it a theory of formidable complexity, especially at low energies, where the interactions become so strong that perturbative methods falter. Instead, scientists rely on computational approaches like lattice QCD, where space-time is discretized into a finite grid. In this digital laboratory, quarks and gluons can be simulated with increasing precision, revealing the masses and properties of hadrons, the behavior of the strong force under extreme conditions, and even the emergence of phenomena like confinement from first principles. These calculations require immense computational power and have become one of the triumphs of modern theoretical physics, showing how numerical experiments can complement and extend the reach of human intuition. In addition to their role within nucleons, Gluons shape the dynamics of particle collisions at high energies. When protons are accelerated to near light speed and smashed together in colliders like the Large Hadron Collider, it is the gluons that dominate the interactions. These high-energy collisions probe the very structure of matter, revealing jets of particles that trace the original paths of quarks and gluons, indirect signatures of their presence and behavior. These events provide crucial tests of QCD, confirming its predictions with remarkable precision and uncovering subtle hints of new physics that may lie beyond the standard model. Gluons also play a central role in the physics of the early universe. In the immediate aftermath of the Big Bang, the universe existed in a state of quark-gluon plasma, a dense, hot soup where quarks and gluons moved freely, unconfined by hadronic boundaries. As the universe expanded and cooled, this plasma condensed into protons and neutrons, setting the stage for the formation of atomic nuclei and the eventual emergence of stars, planets, and life. Modern experiments seek to recreate this primordial state by colliding heavy ions at immense energies, mimicking the conditions of the early universe for a fleeting moment. The resulting quark-gluon plasma is a unique state of matter, one that flows like a perfect fluid with almost no resistance. Studying it offers a window into the birth of the universe and the behavior of matter at the highest energies known. Despite their ephemeral existence and indirect detection, gluons are an essential part of the cosmic story. They are not mere mathematical abstractions, but real entities whose influence is woven into the very structure of the world around us. Every breath we take, every star that shines is a testament to the silent work of gluons, forever binding the pieces of matter into a stable whole. The self-interacting nature of gluons leads to a rich and fascinating phenomenon known as asymptotic freedom. At very short distances, or equivalently at very high energies, the strong force becomes weaker, allowing quarks to behave almost as free particles. This property explains why quarks can move relatively freely inside a proton or neutron at high energies, even though they remain permanently bound at lower energies. The interplay of confinement and asymptotic freedom is a subtle dance, one that ensures both the stability of matter and the possibility of exploring its internal structure in experiments. Yet for all that we understand, mysteries remain. Why is the strong force so much stronger than the electromagnetic force? What deeper symmetries might underlie the color charges of quarks and gluons? And how does this complex interplay of particles and forces fit into a broader, more unified picture of the universe? These questions continue to drive research, pushing the boundaries of our knowledge and hinting at a deeper order that has yet to be fully revealed. As we consider the role of gluons, we are reminded of the profound beauty and interconnectedness of the natural world. These invisible particles, exchanging color charge in a ceaseless ballet, are the glue that holds the visible universe together. They reveal a truth that resonates far beyond the realm of physics, that the most essential forces are often the ones we cannot see directly, yet they shape our lives and the cosmos in ways both subtle and profound. In the quiet spaces between the stars and the dense cores of matter, gluons move unseen, binding the universe into a coherent whole. Their silent work echoes the deep interconnectedness of all things, a reminder that the forces that hold quarks together are akin to the forces that bind us to one another, weaving a universe of endless complexity and quiet wonder. Chapter 6: W and Z Bosons, the heavyweights of the weak force. Among the fundamental forces of nature, the weak nuclear force is perhaps the most enigmatic. It is neither the gentle, infinite reach of gravity nor the electromagnetic dance of charges and light. It is not the confining grip of the strong force, holding quarks in eternal embrace. Rather, the weak force operates on a subtle scale, shaping processes that occur deep within the atomic nucleus and playing a vital role in the cosmic alchemy that sustains the universe. At the heart of this force are the W and Z bosons, particles whose very existence reveals the delicate interplay of mass and interaction that defines the weak force's unique character. Unlike the photon or the gluon, which are massless and travel unimpeded at the speed of light, the W and Z bosons are heavy. Their masses are immense compared to those of other force carriers, more than 80 times the mass of a proton. This heaviness gives the weak force its name. It restricts the range of the force, confining it to the subatomic realm and making it perceptible only in processes that occur on scales smaller than an atomic nucleus. The story of the W and Z bosons begins with the quest to unify our understanding of the forces of nature. In the mid-20th century, physicists began to see hints that the electromagnetic force and the weak force, though so different in their manifestations, might be two facets of a single, deeper interaction. This idea of electroweak unification was a radical departure from classical physics, a merging of forces that had long been considered distinct. In this unified picture, the W and Z bosons arise naturally, emerging as the mediators of the weak interaction. The W bosons, with their electric charge, either positive or negative, enable processes in which particles change their identity, transforming one type of fundamental particle into another. The Z boson, electrically neutral, is responsible for neutral current interactions, subtle processes where particles exchange energy without changing their fundamental type. Together, they embody the dual nature of the weak force, one that both changes and conserves identity. The weak force's ability to transform particles is essential to the workings of nature. In the core of stars, where hydrogen fuses into helium and powers the light of the universe, it is the weak force that enables the conversion of protons into neutrons, a transformation that releases energy and sustains the radiance of the sun. Without the weak force, the stars would be dark, the cosmos static and inert. Yet the weak force is also a force of decay. It governs beta decay, the process by which neutrons transform into protons, electrons, and neutrinos, a transformation that powers nuclear reactions and shapes the evolution of elements in the universe. In the radioactive decay of heavy elements on Earth, in the slow ticking of atoms in our bones, the W and Z bosons move unseen, mediating the transformations that echo through the ages. The discovery of the W and Z boson stands as a testament to the power of both theoretical insight and experimental ingenuity. The standard model of particle physics predicted their existence decades before they were seen, weaving them into the fabric of electroweak unification. But it was only in the early 1980s, at the CERN laboratory near Geneva, that these particles were directly observed. In high-energy collisions of protons and antiprotons, the W and Z bosons revealed themselves as fleeting bursts of energy, their presence confirmed by the particles they decayed into. Their discovery was a triumph not just of technology, but of vision. It showed that the forces of nature, though they appear different in the world we see, are unified at a deeper level, their differences emerging only through the subtle breaking of symmetries that give rise to the richness of the cosmos. The mass of the W and Z bosons is a key feature of their role. In the Standard Model, particles acquire mass through their interactions with the Higgs field, a pervasive field that fills all of space. The W and Z bosons couple strongly to this field, and it is this interaction that endows them with their substantial masses. In contrast, the photon does not interact with the Higgs field and remains massless, able to travel across the universe unimpeded. The interplay of the W and Z bosons with the Higgs field is a profound illustration of how mass and force are intertwined. The heaviness of these bosons ensures that the weak force is short-ranged, confined to the intimate spaces of the nucleus. It also ensures that the processes they mediate are rare and fleeting, occurring with a delicacy that belies their fundamental significance. In the realm of particle physics, the W and Z bosons are more than just mediators of force. They are signatures of the deep symmetries that underlie the world. Their interactions are described by the electroweak theory, a framework that unifies the electromagnetic and weak forces into a single elegant structure. This unification is not visible in the low-energy world of daily life, where the weak force seems so different from the familiar magnetism of a refrigerator or the glow of a light bulb. But at high energies, such as those that existed in the early universe, the distinction vanishes, revealing a symmetry that binds the forces together. This symmetry, known as electroweak symmetry, is spontaneously broken in the universe we inhabit today. It is this breaking that gives mass to the W and Z bosons and that distinguishes the photon from its heavier siblings. In this breaking, we see the emergence of diversity from unity, a theme that resonates not just in physics, but in the broader patterns of nature. The W and Z bosons also play a role in processes that probe the boundaries of known physics. Precision measurements of their masses, lifetimes, and interactions provide stringent tests of the standard model, revealing tiny discrepancies that could be hints of new physics waiting to be discovered. In the laboratories of CERN, Fermilab, and other research centers, physicists measure these properties with ever greater accuracy, seeking the faint echoes of forces and particles that might extend beyond the current horizon of knowledge. Beyond their role in fundamental interactions, the W and Z bosons also serve as probes of the early universe. In the hot, dense plasma of the primordial cosmos, these bosons would have moved freely, their interactions shaping the balance of matter and antimatter, the seeds of the galaxies that now light the night sky. Their presence in the equations of the early universe is a reminder that even the fleeting, the ephemeral, leaves a lasting imprint on the structure of reality. In modern experiments, the W and Z bosons are produced in the collisions of high-energy particles, their decays recorded in detectors as flashes of light and showers of secondary particles. These collisions recreate, for a brief instant, the conditions of the universe's earliest moments, allowing physicists to study the behavior of matter and energy at scales that approach the dawn of time. These experiments are not mere technical exercises. They are acts of discovery, glimpses into the processes that govern the cosmos at its most fundamental level. They reveal the extraordinary unity of the forces that shape our world and hint at the mysteries that still lie beyond the reach of current theory. In reflecting on the W and Z bosons, we are reminded of the delicate balance that sustains the universe. These massive, ephemeral particles are both messengers and creators, mediating the transformations that allow stars to shine and matter to evolve. They are a testament to the subtlety of the natural world, where even the most fleeting interactions have consequences that echo across the eons. As we stand at the edge of the known, contemplating these heavy weights of the weak force, we find a quiet wonder in their existence. They are a reminder that the universe is not built from static pieces, but from dynamic relationships, that even the briefest moment of transformation can shape the course of the cosmos. In their fleeting lives, the W and Z bosons reveal the profound truth that everything is in motion, everything is in flux, and that in this motion lies the beauty and mystery of the universe itself. Chapter 7. The Higgs boson, giving mass to the world. Among the tapestry of particles that define the quantum realm, the Higgs boson holds a unique place. It is not a carrier of force like the photon or gluon, nor a constituent of matter like quarks and electrons. Instead, the Higgs boson stands as a key to understanding one of the deepest mysteries of modern physics, the origin of mass itself. Its discovery in 2012 confirmed a mechanism that had long been theorized, yet it also opened the door to questions that touched the very structure of reality. At its heart, the Higgs boson is a quantum excitation of the Higgs field, a pervasive field that permeates all of space. This field is unlike the electric and magnetic fields we encounter in daily life. It is ever-present, uniform, and unbroken, woven into the very fabric of the universe. Through its interactions with fundamental particles, it imparts mass, granting substance to the ephemeral quanta that dance through the void. To understand the role of the Higgs boson, one must first recognize the nature of mass in the quantum world. In classical physics, mass is an intrinsic property, a measure of an object's inertia and its response to gravity. But in the quantum domain, where particles are excitations of underlying fields, mass arises from interactions. Particles are not isolated entities, but are defined by their relationships with the fields that surround them. The Higgs field, in this context, acts as an invisible medium that endows certain particles with mass through their coupling to it. This coupling varies depending on the particle. The W and Z bosons of the weak force, for example, interact strongly with the Higgs field and acquire large masses, while the photon, which does not couple to the Higgs field at all, remains massless. Fermions such as quarks and electrons also gain mass through their interactions with the Higgs field, with the strength of this interaction determining the masses of these particles. The idea that mass emerges from interaction rather than from intrinsic properties was a revolutionary insight in the 1960s, when Peter Higgs, along with Robert Brute, Francois Englert, and others, proposed the mechanism that now bears Higgs' name. They showed that if the Higgs field exists and has a non-zero value everywhere in space, it would break the electroweak symmetry of the Standard Model, explaining how the weak force can have massive mediators while the photon remains massless. The Higgs field's non-zero value, its so-called vacuum expectation value, is what distinguishes our universe from one that is perfectly symmetrical and massless. In a world without the Higgs field, particles would move at the speed of light, unable to form atoms or structures. Chemistry, biology, and the richness of the cosmos would be impossible. The Higgs field's presence, constant and silent, allows for the emergence of the complexity we see in nature. The Higgs boson itself is the quantum ripple in this field, a particle whose existence confirms the reality of the field it represents. It is as if the calm, invisible ocean of the Higgs field can momentarily be disturbed, creating a crest of energy that propagates as a particle, the Higgs boson. Unlike the photon or gluon, which are constantly in motion, the Higgs boson is massive, ephemeral, and rare, existing only briefly before decaying into lighter particles. The search for the Higgs boson was a monumental effort, spanning decades and requiring some of the most sophisticated experiments ever constructed. At the Large Hadron Collider near Geneva, protons are accelerated to nearly the speed of light and smashed together with energies that recreate conditions similar to those that existed just moments after the Big Bang. In these collisions, energy can briefly be converted into mass, creating particles like the Higgs boson in a fleeting dance of creation and decay. Detecting the Higgs boson required tracking the particles it decays into, piecing together its presence from the showers of energy and matter recorded by enormous detectors. These instruments, towering structures of metal and silicon, are designed to capture the subtlest hints of the quantum world, revealing the footprints of particles that exist for only trillionths of a second. When the discovery was announced in 2012, it marked a triumph not only of experimental precision, but also of human curiosity and perseverance. The detection of the Higgs boson was the final confirmation of the Standard Model, the framework that describes the known particles and forces with exquisite accuracy. Yet it was also a beginning, hinting at a deeper layer of reality that remains to be fully understood. The mass of the Higgs boson itself, measured at about 125 giga-electron volts, carries profound implications for the stability of the universe. Calculations suggest that this mass places our cosmos in a delicate balance, a metastable state that could, in principle, one day transition to a different vacuum state. This possibility, while distant and theoretical, underscores the fragility and wonder of the universe we inhabit, a universe balanced on the knife's edge of quantum forces and fields. The Higgs field does not grant mass to everything. The masses of protons and neutrons, for example, arise mostly from the dynamic energy of quarks and gluons interacting through the strong force. Yet for the fundamental particles themselves, the quarks, the charged leptons, and the W and Z bosons, the Higgs field is the source of their mass. Without it, the rich hierarchy of particle masses, the diversity of elements, and the structure of galaxies would not exist. The study of the Higgs boson continues to this day as physicists probe its properties with increasing precision. Is the Higgs boson exactly as the Standard Model predicts, or are there subtle deviations that hint at new forces or particles? Does it interact with particles we have yet to discover, perhaps those that make up the dark matter that pervades the cosmos? These questions drive ongoing experiments, turning the Higgs boson from a confirmed discovery into a tool for exploring the unknown. In the quiet hum of particle accelerators, in the whir of detectors cooled to near absolute zero, physicists listen for the whispers of the Higgs boson. Each new measurement refines our understanding, closing some doors while opening others, revealing the richness of a universe that is both knowable and full of mystery. Beyond its scientific significance, the Higgs boson stands as a testament to the human spirit of inquiry. Its discovery required the collaboration of thousands of scientists, engineers, and thinkers from around the world. It required the building of machines of almost unimaginable complexity, instruments that push the limits of technology and ingenuity. In this effort, we see not just the search for knowledge, but the weaving together of minds and cultures, a reflection of our shared curiosity and capacity for wonder. As we contemplate the Higgs boson, we find a particle that is at once humble and profound. It is a silent partner in the dance of the cosmos, a gentle field that gives weight to the world. It is a reminder that mass itself, the stuff of mountains and oceans, of planets and people, emerges from something deeper, an invisible field that permeates all of existence. In the quiet spaces of the universe, where galaxies drift and stars burn, the Higgs field moves unseen, shaping the weight and texture of matter. Its gentle presence is a testament to the idea that what we perceive as solid and immutable is, at its heart, a dynamic interplay of fields and interactions. The Higgs boson, the fleeting crest of this invisible ocean, reveals the quiet power of the quantum world, a world where the intangible becomes tangible, where the emptiness of space is filled with possibility. As we draw this chapter to a close, let us pause to reflect on the deeper meaning of the Higgs boson. It is more than a particle or a field. It is a window into the unity and subtlety of nature. It teaches us that the most fundamental aspects of reality are not always the most visible, that the weight of the world arises from the whisper of an invisible field. In this gentle presence, we find a metaphor for the quiet forces that shape our own lives, unseen yet essential, humble yet profound, a testament to the endless wonder of the cosmos and our place within it. Chapter 8. Gravitons, the elusive quantum of gravity. Among the four fundamental forces that govern the universe, gravity holds a unique and paradoxical position. It is at once the most familiar and the most enigmatic. It is the force that binds us to the Earth, that steers the planets in their orbits, and that shapes the grand architecture of galaxies and galaxy clusters. Yet, when we attempt to describe it in the quantum terms that successfully explain the other forces, gravity remains elusive, resisting incorporation into the Standard Model and defying direct quantization. In the search for a quantum theory of gravity, the graviton emerges as a tantalizing idea, a hypothetical particle that could be the quantum mediator of gravitational interactions. The concept of the graviton arises naturally from the desire to treat gravity on the same quantum footing as the electromagnetic, weak, and strong forces. In those forces, interactions are carried by exchange particles, photons, W and Z bosons, gluons, each transmitting the corresponding force through quantum interactions. By analogy, the gravitational interaction should also have a mediator, a massless spin-2 particle called the graviton. Unlike the photon, which mediates the electromagnetic force, the graviton would carry the subtle distortions of spacetime itself. In Einstein's general theory of relativity, gravity is not a force in the traditional sense, but a manifestation of the curvature of spacetime caused by mass and energy. Objects follow the paths determined by this curvature, creating the illusion of a force that pulls them together. The graviton, in the quantum picture, would be the quantized vibration of this spacetime fabric, a tiny ripple that travels at the speed of light, communicating the pull of gravity across the cosmos. The graviton's properties are inferred from the symmetries and requirements of quantum field theory. As a spin-2 boson, it would couple to energy and momentum rather than electric charge or color. Its masslessness ensures that gravity has an infinite range, just as the photon's masslessness allows light to travel freely across the universe. Yet unlike the photon, the graviton has never been directly detected. Its existence remains theoretical, a logical extension of the framework of quantum physics rather than an experimental reality. The challenge of detecting gravitons lies in the inherent weakness of the gravitational interaction. Gravity is a force that dominates on cosmic scales, yet on the scale of particles, it is vanishingly small compared to the other interactions. The energy carried by a single graviton would be so minute that any attempt to observe it directly would be drowned out by the cacophony of other processes, the quantum noise of the universe itself. This near impossibility of direct detection has turned the search for gravitons into a frontier of theoretical and indirect experimental work. Instead of seeking individual gravitons, physicists explore the quantum nature of gravity through the ripples of spacetime known as gravitational waves. First predicted by Einstein's theory of general relativity, these waves are distortions in spacetime that propagate outward from massive, accelerating bodies. The discovery of gravitational waves by the LIGO Observatory in 2015 confirmed their existence, opening a new window on the universe and earning a Nobel Prize for the pioneering work. Gravitational waves, though classical in their current detection, are believed to be composed of countless gravitons in the quantum picture, much as a beam of light can be seen as a collection of photons. Observing the granular, quantum nature of these waves would be a profound step, though the energies and precision required lie far beyond our current technological capabilities. In this sense, the graviton remains both a guiding concept and an elusive target, a symbol of the incomplete union of quantum theory and gravity. The search for a quantum theory of gravity goes beyond the graviton itself. It involves weaving together the principles of general relativity, which describes the smooth curvature of spacetime, and the principles of quantum field theory, which describe the jittery dance of particles and fields at the smallest scales. This synthesis, still incomplete, is one of the greatest challenges of modern physics, a puzzle that has inspired decades of research and countless theoretical frameworks. One of the most prominent approaches is string theory, which suggests that all fundamental particles, including the graviton, are not point-like, but are instead tiny vibrating strings. In this view, the graviton naturally emerges as one of the vibration modes of the string, offering a graceful unification of quantum mechanics and gravity. String theory provides a mathematically consistent framework that can incorporate gravity, yet it remains beyond the reach of direct experimental tests. existing more as a beautiful possibility than a confirmed theory. Another promising avenue is loop quantum gravity, which takes a different path by attempting to quantize spacetime itself, treating the geometry of the universe as woven from discrete loops. In this approach, gravitons would arise as excitations of these loops, though the details are still being worked out in ongoing research. Despite these efforts, the union of gravity and quantum mechanics remains an open frontier. The graviton, as a particle, sits at the crossroads of these two great theories, a symbol of the unity that physicists seek. If it exists, it would embody the quantum nature of the most familiar force, revealing that even the pull of gravity is part of the quantum dance that underlies all of reality. The implications of a quantum theory of gravity would be profound. It would allow us to describe the physics of the very early universe, moments after the Big Bang, when the known forces were unified in a searing plasma of energy and possibility. It would illuminate the hearts of black holes, where gravity and quantum effects collide in a maelstrom of mystery. And it would reshape our understanding of space-time itself, revealing it not as a passive backdrop, but as a dynamic, fluctuating entity subject to the same uncertainty and superposition that govern the quantum world. The search for gravitons is more than a technical quest. It is a journey into the very nature of reality, a reflection of our desire to see the universe as a coherent whole rather than as a collection of separate pieces. In the graviton, we see the possibility that the forces that move the planets and the forces that bind quarks are different expressions of the same cosmic principles, woven together by the mathematics of quantum fields and the geometry of space-time. Yet this search also humbles us. For all the power of our theories and the reach of our instruments, the graviton remains beyond our direct grasp, a ghostly presence that hints at the limits of our knowledge. It challenges us to think not only about what is measurable, but about what is meaningful. To consider that the deepest truths may lie not in the particles we can count, but in the relationships and symmetries that shape the universe at every scale. In reflecting on the graviton, we are reminded that science is as much about the questions as the answers. The graviton may or may not be discovered in our lifetime, but the search itself enriches our understanding of the cosmos and our place within it. It reminds us that the universe is a tapestry of mysteries, each thread leading deeper into the unknown, each discovery opening new vistas of wonder. As we contemplate the graviton, let us take a moment to appreciate the quiet elegance of this hypothetical particle. In its suggestion of a quantum gravity, it whispers of a universe where even the pull of the Earth and the birth of stars are part of the same cosmic story. In its elusiveness, it teaches us patience and humility, a reminder that while the universe may yield its secrets slowly, each step of the journey brings us closer to a deeper understanding of the profound unity that lies at the heart of all things. Chapter 9. Beyond the Standard Model. Are there smaller pieces still? The Standard Model of particle physics stands as one of the crowning achievements of modern science. It elegantly describes the zoo of fundamental particles and the forces that govern their interactions, weaving together a tapestry that accounts for everything from the structure of the atom to the processes that power stars. Yet, even in its precision and consistency, the Standard Model is incomplete. It is a remarkable yet partial map of reality, one that leaves profound questions open and hints at deeper layers of structure and possibility. One of the most striking limitations of the Standard Model is its inability to incorporate gravity into its framework. While it has successfully unified the electromagnetic, weak and strong interactions, gravity remains outside its reach, described instead by Einstein's general theory of relativity. General relativity, with its elegant depiction of space-time as a dynamic, curved entity, operates in a classical domain. It speaks of geometry and curvature, not of quanta and uncertainty. Reconciling gravity with quantum mechanics is one of the deepest challenges in theoretical physics, an endeavor that would reveal how the very fabric of the cosmos behaves at its smallest scales. The search for a quantum theory of gravity has led to tantalizing approaches like string theory and loop quantum gravity. String theory suggests that the fundamental constituents of the universe are not point-like particles, but one-dimensional vibrating strings, their oscillations giving rise to the myriad particles we observe. This framework naturally accommodates gravity, proposing that the graviton, the hypothetical quantum of gravity, is one of the string's many vibration modes. Loop quantum gravity, by contrast, envisions space-time itself as composed of discrete loops, quantized at the smallest scales. These approaches are mathematically rich and promising, yet they remain beyond the reach of direct experimental confirmation, their predictions still awaiting the touchstone of observation. Beyond the question of gravity, the Standard Model also fails to account for the enigmatic dark matter that pervades the universe. Observations of galactic rotation curves and the gravitational bending of light around clusters of galaxies suggest the presence of an invisible mass that outweighs visible matter by a factor of 5. This dark matter does not emit or absorb light, nor does it interact strongly with known particles, eluding all attempts at direct detection. The Standard Model, for all its triumphs, offers no explanation for this unseen mass. Physicists have proposed extensions that introduce new particles, weakly interacting massive particles, WIMPs, sterile neutrinos, or axions, that could compose this dark matter, but their existence remains unconfirmed. The imbalance between matter and antimatter in the universe is another mystery that the Standard Model cannot fully resolve. According to its rules, the early universe should have contained equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a sea of radiation, but no matter to form stars, planets, or life. Yet, the observable cosmos is filled with matter, with only trace amounts of antimatter found in cosmic rays and high-energy processes. This asymmetry suggests that there must be additional processes beyond those accounted for in the Standard Model that favor matter over antimatter, tipping the cosmic balance in our favor. Neutrino physics has also forced us to look beyond the Standard Model. For decades, neutrinos were thought to be massless, ghost-like particles that rarely interacted with matter. But experiments observing the oscillations of neutrinos between different types have shown that they must possess mass, however small. This discovery requires a modification of the Standard Model, hinting at the existence of right-handed neutrinos or other mechanisms that can endow these elusive particles with their subtle weight. The seesaw mechanism, which introduces heavy neutrino partners, offers one elegant explanation, though it too remains a topic of ongoing investigation. Another puzzle is the hierarchy problem, which asks why the Higgs boson's mass is so much smaller than the scale at which gravity becomes significant. Quantum corrections to the Higgs mass tend to push it up to enormous values, far beyond what is observed. To keep the Higgs mass at its measured value requires an extraordinary degree of fine-tuning, a situation many physicists find unnatural. Supersymmetry, a proposed extension of the Standard Model, offers a possible solution by introducing partner particles that balance out these quantum corrections, preserving the stability of the Higgs field. Supersymmetry also provides natural candidates for dark matter, intertwining these mysteries in a single elegant framework. Grand unified theories, GUTS, take the ambition even further, seeking to merge the electromagnetic, weak, and strong forces into a single force at high energies. Such unification would reveal a profound simplicity beneath the apparent complexity of the particle world, suggesting that the diverse interactions we observe today are mere echoes of a deeper unity. Guts predict the existence of new particles and processes such as proton decay that have yet to be observed, providing a rich field for experimental tests and a roadmap for future discoveries. Experimental hints of physics beyond the standard model have begun to appear in subtle ways. Measurements of the magnetic moment of the muon show a small discrepancy with theoretical predictions, suggesting that new particles or forces may be at play. Similarly, observations of rare decays of B mesons have shown patterns that deviate from standard model expectations, tantalizing clues that there may be new interactions waiting to be uncovered. These anomalies are not yet definitive, but they provide a sense of excitement, a whisper that the standard model, magnificent as it is, may be only a chapter in the deeper story of the universe. The possibility that there are smaller, more fundamental pieces of nature than the quarks and leptons of the standard model is both humbling and exhilarating. Are there layers beneath these particles, as atoms once gave way to nuclei and nuclei to quarks? Could the next step reveal a deeper unity or a new symmetry that binds the known forces and particles into an even more elegant whole? These questions drive the work of theorists and experimentalists alike, pushing the boundaries of knowledge and inspiring new generations of physicists to probe the limits of the known. As we pursue these questions, we also confront the limitations of our instruments and our imagination. The energy scales at which new physics might emerge lie far beyond what current colliders can achieve. Future accelerators, more powerful and precise, may be needed to glimpse the next layer of reality. In parallel, creative theoretical approaches and innovative detectors seek to capture the faint signals of dark matter or the rarest decays that might reveal hidden structures. The search for physics beyond the standard model is not merely a quest for more particles or more data. It is a journey into the nature of existence itself. It challenges our understanding of space and time, of matter and energy, of what it means for something to be fundamental. It invites us to imagine that even the most familiar particles, quarks, electrons, neutrinos, are not the final story, but the opening notes in a cosmic symphony that stretches to infinity. In the end, these questions remind us that our understanding of the universe is always provisional, always open to revision and expansion. The standard model is a magnificent framework, but it is also a reminder of the human impulse to see beyond the horizon, to ask what lies behind the curtain of the known. As we explore the possibilities that lie beyond it, we participate in an ancient and ongoing tradition, the search for the ultimate building blocks of nature, the quest to know how we and the universe are woven from the same cosmic threads. In these reflections, there is a quiet humility. For all our equations and experiments, we know that each answer only opens new doors, each discovery only deepens the mystery. And in that endless journey, ever unfolding, ever expanding, we find not only the secrets of particles and forces, but also the echo of our own curiosity and the reminder that we, too, are part of this wondrous and unfinished story. Chapter 10. Conclusion. The never-ending search for simplicity. The search for the fundamental constituents of nature is as old as human curiosity itself. From the earliest philosophers who pondered what lies beneath the visible world, to the modern physicists who peer into the heart of matter with colossal machines and precise mathematics, the desire to understand the universe's building blocks is woven into the human story. It is a quest to uncover simplicity amid complexity, to find patterns and unities in the swirling dance of particles and forces that make up everything we see. At each step, this search has revealed unexpected elegance. The atom, once thought to be indivisible, gave way to the nucleus and the electron. The nucleus itself, so dense and seemingly solid, was found to be made of protons and neutrons, bound in a delicate balance of forces. Protons and neutrons, in turn, revealed the presence of quarks, interacting through the strong forces gluons, and joined by leptons like the electron and the neutrino. Each layer, once considered final, has turned out to be another step on the path. Each discovery both a triumph and a tantalizing clue that there is more to learn. This pursuit of the smallest pieces is not driven solely by the desire to catalog the world's particles. It is a search for the principles that underlie the cosmos, for the hidden symmetries that govern the transformations of matter and energy. The Standard Model stands as a testament to this effort, a framework of extraordinary predictive power, uniting the electromagnetic, weak, and strong forces, and describing the behaviors of all known fundamental particles with stunning accuracy. Yet even as we celebrate the Standard Model's successes, we see the questions it cannot answer. The gravitational force, so familiar in the fall of an apple or the orbits of planets, eludes quantization. Dark matter, inferred from the motions of galaxies and the bending of light, floats unseen beyond the reach of known particles. Dark energy, driving the accelerating expansion of the universe, remains a cosmic mystery, a silent force pulling at the fabric of space-time itself. These gaps remind us that our current theories, powerful as they are only approximations of a deeper reality. They hint at layers yet unprobed, at symmetries yet unbroken, at principles that lie just beyond the reach of today's colliders and detectors. In these mysteries, the search for simplicity becomes the search for a deeper unity, one that transcends the distinctions between matter and energy, between forces and particles, between what is known and what remains to be discovered. This search has also taught us that simplicity does not always mean ease of understanding. The equations of quantum field theory, the renormalization of infinities, the self-interactions of gluons, and the dynamic nature of the vacuum itself, these are not simple in the everyday sense. Rather, simplicity in physics means a framework that, despite its apparent complexity, reveals an underlying coherence, a set of rules from which the intricate diversity of the cosmos emerges. The Higgs field, with its invisible yet ever-present influence, is one such example. It reveals that what we perceive as mass is not an inherent property, but a result of interactions, a dance between particles and fields that plays out in the emptiness of space. Similarly, the concept of color charge in quarks, though abstract, ensures that the strong force can build the heavy nuclei that fuel the stars, the same stars that forge the elements in our bodies. These insights do more than enrich our understanding of physics. They shape how we see the world around us. They remind us that everything we see, the light of a candle, the warmth of the sun, the solidity of the earth beneath our feet, is the result of processes at scales far beyond our senses. The world is not made of immutable pieces, but of relationships, of fields and forces interacting in ways both subtle and profound. As we look to the future, the questions that remain are as inspiring as those we have answered. Will we find evidence for supersymmetry, a symmetry that could explain the stability of the Higgs field and provide a candidate for dark matter? Will string theory, with its higher dimensions and vibrating filaments, offer a glimpse of a unified description of gravity and quantum mechanics? Will we uncover new particles that fill the gaps in the Standard Model or hint at entirely new frameworks for understanding the universe? These questions drive the experiments of today and tomorrow. The colliders that accelerate particles to near light speeds, the detectors buried deep underground to catch the faint whispers of dark matter, the gravitational wave observatories that listen for ripples in space-time. All these efforts are steps on the same path. They are the tools with which we probe the foundations of reality, extending our reach from the smallest quanta to the largest structures of the cosmos. But the search for simplicity is not limited to the laboratory or the blackboard. It is also a reflection of the human spirit. It mirrors our desire to see the world not as a collection of isolated parts, but as a connected whole, governed by principles that transcend the apparent chaos of daily life. It is the drive to find order in the night sky, to see the elegance of nature's laws in the growth of a tree or the orbit of a planet. Each breakthrough in physics, from the discovery of the electron to the detection of the Higgs boson, has expanded our view of what is possible. It has shown us that nature's simplicity is not the simplicity of stillness, but the simplicity of pattern, the hidden symphony of quanta and fields that sings the universe into being. At the same time, each new layer we uncover challenges our intuition, forcing us to let go of old notions and embrace new paradigms. Quantum mechanics teaches us that certainty and determinism give way to probabilities and uncertainties, that particles can be both waves and corpuscles, that the very act of observation changes what is observed. General relativity shows us that space and time are not passive backgrounds, but active participants in the cosmic drama. In these lessons, we find a deeper kind of simplicity, one that acknowledges the limitations of our perception and the richness of the universe beyond it. We learn that simplicity does not mean easy answers, but the elegance of principles that can account for the complexity of the world. As we contemplate the path ahead, we recognize that the search for simplicity is a never-ending journey. It is a journey that has no final destination, for each answer opens new questions. Each discovery reveals new mysteries. It is a journey that mirrors the unfolding of the cosmos itself, an endless expansion of understanding that reflects the infinite richness of the universe. In the end, perhaps this is what makes the search for simplicity so profoundly human. It is an expression of our curiosity, our drive to see beyond the visible, to ask what lies beneath the surface. It is a testament to our capacity to wonder, to imagine, to dream. And in that capacity, we find not only the key to understanding the particles and forces that shape the world, but also a reflection of our own place in the cosmos. For in every experiment and every theory, in every question asked and every answer found, there is a quiet echo of the same truth, that the universe is more than a collection of things. It is a story, a song, a dance, an unfolding tapestry of patterns and relationships that bind the smallest quanta to the vastest galaxies and us in our small corner of space and time to the whole. In the gentle quest for simplicity, we glimpse the possibility that everything is connected, that beneath the noise and chaos, there is a harmony waiting to be revealed. And in that harmony, we find both the humbling limits of our knowledge and the endless wonder of what it means to be a part of this vast, beautiful, and ever-expanding universe. Thank you for joining this soothing exploration of the smallest pieces of nature. If you're still awake, consider watching another video to continue your quiet journey through the cosmos. And if you've drifted off, may your dreams carry you deeper into the mysteries of the universe. Sleep well and sweet dreams among the stars.